Hello divers, and welcome to our channel, The Diving Method. Today's video, which counts 2 episodes, is about what we could call the physics of gases in scuba diving. We are referring to the laws we have learnt during our open water course, therefore the laws of Boyle, of Henry, of Dalton, of Charles, and the Guy-Lussac ones. These laws have confused more than one beginner diver, and often, a few weeks after the conclusion of the open water course or equivalent, the only law we still remember is Boyle's. And sometimes we just remember its main implication, maybe without even remembering its name. Of course, names are not as important as the implications, and this video is not a detailed explanation of these laws, which can surely be found in our diving manuals. It's more a practical connection of them to our dives. Now, as certified divers with some practical experience under our belt, we can probably better connect this theory to the relative practice, and maybe even to some episodes we might have encountered.
The combined law of gases involves 3 different laws that are based on the same 3 different parameters of a given gas: the pressure, the volume, and the temperature. Each law keeps one of these parameters fixed, defining the correlation of the other 2 as one vary, and for our purpose, this is a possible classification. The Boyle's law, which keeps the temperature fixed, while pressure and volume vary. The Charles law, which instead keeps the pressure fixed, while temperature and volume vary. And last but not least, the Guy-Lussac's law, which keeps the volume fixed, while temperature and pressure vary. This law is sometimes also called Charles and Guy-Lussac's law. In diving theory, Henry's law, as well as the Dalton's ones, play important roles too.
To better understand these 3 laws, we need to be clear about the difference between flexible and rigid containers. A rigid container is a gas container strong enough to withstand pressure, without changing its shape and volume. 3 examples of rigid containers are a submarine, or closer to our dives, our cylinder, and the waterproof housing of our camera. On the other hand, a flexible container is a gas container unable to withstand increasing or decreasing pressure without changing its shape. Examples of flexible gas containers are lungs, our ears and paranasal sinuses, stomach and intestine, plus mask, BCD, dry suit, and SMB.
For recreational divers' purpose, which we are, we always assume that the temperature of the gas remains constant during the whole dive. The temperature of the used gas is strictly correlated with the water temperature, and even though we know that the temperature can vary a lot during the same dive, making, for example, the passage through a thermocline more or less comfortable, for many purposes, this effect cannot change much the numeric considerations and the procedures we have to apply. As recreational divers, concepts are more important than extremely precise mathematics and numbers, and this simplification allows us to refer to the easier Boyle's law to learn about the gas volume variations, and then to apply it to several situations. Boyle's law, also known as the law of pressures and volumes, can be easily summarized by saying that when the pressure increases, the gas volume decreases, and vice versa. When the pressure decreases, the gas volume increases. They are inversely proportional. And of course, we know from other bits of study that increasing pressure means we are moving down in the water column, toward the bottom, while decreasing pressure means we are moving up toward the surface.
Practically speaking, the Boyle's law affects any flexible container, and therefore, it is also related to the most important rule we have learned to respect: never hold our breath. The law says that the inhaled gas at one depth will expand its volume when ascending. Boyle's law advises us that we may suffer from reverse block and injuries if, for any reason during ascent, the expanding gas is not free to exit from confined space, such as lungs, ears, nasal and paranasal sinuses, stomach, and intestines, while if the trapped gas is in the BCD or dry suit, we might lose control of our ascent. In the opposite direction, it also states that to prevent any form of squeeze, we need to equalize our ears, mask, and dry suit while descending.
Due to the fact that our neutral buoyancy is also strictly related to the volume of gas in our BCD, it also states that changing our depth will also change this volume, and we might need to add or release gas. Boyle's law also explains why our neoprene diving suit, which contains cells of gas, becomes thinner and thinner when descending, losing its thermal protective characteristics and its typical positive buoyant status. And consequently, this is also one of the reasons why a weight belt becomes looser in deeper water.
Boyle's law also explains why it is not necessary to fully inflate an SMB before throwing it, and why it is easier to deploy it in deep water than in shallower water. The gas introduced at one depth will expand its volume during the ascent, hopefully fully filling it. The deeper we release the gas into the SMB, the greater the pressure reduction during the ascent, and consequently, the larger the gas volume when it reaches the surface. If we are deep enough, we only need a small amount of gas to trigger the SMB ascent. Then, the pressure reduction will expand the gas volume, fully filling it. If we are not deep enough, the gas will not have the opportunity to expand enough. In this case, we might need to inflate the SMB more before lift it, forcing us to pull down a buoyant item until the introduced gas reaches a sufficient amount.
Another practical situation in which Boyle's law sometimes plays a crucial role is when we wear a hood on top of our mask. Often, some mask-escaping air moves inside the hood. If this happens, and if the air does not find a way to escape from the hood, it will expand inside it, adding a significant source of positive buoyancy that can lead to discomfort or sometimes difficulties in keeping the desired depth. This is the reason hoods have holes on top, or if they don't, is the reason why divers make these holes.
Some divers might have experienced more difficulty managing their buoyancy or air equalization in shallow water than in deep water, and in both cases, Boyle's law could be involved. The change in gas volume due to the pressure variation is not linear, meaning it does not occur to the same extent at all depths, and at some depths is more pronounced than at others. Passing from 40 to 30 meters will not have the same effect as passing from 10 meters to the surface. While the difference in depth is always 10 meters, and the pressure reduction is 1 bar in both cases, in terms of percentage, there is a big difference, which also means a big difference in the final effect. From 40 to 30 meters, the pressure varies from 5 to 4 bars, with a reduction of 1/5, or 20%. This means the volume of gas will increase by 1/5, equal to 20% more than the original volume. But from 10 meters to the surface, the pressure varies from 2 to 1 bar, with a reduction of 1/2, or 50%. This means the volume of gas will double, or be 100% more than the original volume. This is the reason why the range from the surface down to 10 meters is particularly tricky, especially for beginner divers, and of course, in a reverse mode, the same happens moving from the surface toward the bottom.
Here ends the first episode of this series of 2. Thank you for watching, and see you in the next one to finish discussing the remaining laws and some practical uses. Please find the link to the second episode in the description. Remember that clicking on the bell and subscribing will keep you informed about new videos. By sharing and giving a like to this video, you will help spread greater awareness among divers.